Hi, in this lecture, let's go ahead and derive the wave equation that describes the propagation of sound waves. Now, what are sound waves? They are actually longitudinal pressure waves, and they require matter to propagate, albeit air, liquid, or a solid. So what do we mean by a longitudinal pressure wave? So I've got some material, perhaps indicated by this slinky here, and the sound wave is a longitudinal wave that propagates along the direction of motion through the material. So if I give it a little kick on one side, I have a wave that will propagate from one side to the other and back and forth because it will reflect off of each hand. So I've got a longitudinal pressure wave. It's compressing and expanding the slinky as it's traveling in a certain direction. So that propagation goes in the same direction as the compression and expansion. But it does require matter to propagate. So if you're in the vacuum of space, there is no sound, unlike perhaps some sci-fi movies, which you hear the explosions in space. But as correct in some other older sci-fi movies, in space no one can hear you scream, and that's true because there's no sound propagation in vacuum. All right, but let's go on with the lecture. So as I said, sound waves are an alternating compression and expansion. That expansion part is also known as rarefaction. And so if I have a drawing here to kind of work from, imagine we've got a tube. We'll make it a cylindrical tube of some cross-sectional area A. And we've got air in it, say. That'll be indicated by a volume element delineated by the solid lines here, which have a width of delta x. And to get a sound wave, we need a change in pressure around that volume element. So the pressure might be P on the left side, and it'll be a different pressure, P plus delta P on the right side. Delta P could be plus or minus, but I wrote as plus delta P here. And what happens is if I got different pressure on the right side than the left side, then the two edges of that volume of air would have different forces from the different pressures acting on them. And so the volume of that element of air will change. And so we'll discuss that now in some detail to set up this wave equation. Okay, so there's the same drawing. So we're going to consider the oscillation displacement of a small fluid element along the x-axis. So my fluid element, I'm going to give it a position here, position S, and it depends on x and t. X will be along the horizontal direction, and t, of course, is time. And I should have made it clear that these longitudinal pressure waves, although the pressure wave might be moving in the x-axis from left to right, it's not like the whole slinky got thrown from left to right or right to left. There's an oscillation of each element there as the wave passes through. So the wave is oscillating, plus and minus along that x-axis. It's not actually moving as you have described in, say, in a mechanics class. All right, so the horizontal displacement of this fluid element, which is time dependent, will be labeled by that position S, which depends on x and t, as I said. All right, we'll need the volume of this fluid element. So if we've got a tube of cross-sectional area A, and the nominal width of that element of air is delta x, then A times delta x is the volume. I'm going to assume that this volume, this element of air is rather small, so I'm going to give it a delta symbol, just indicates kind of a small volume, and you'll see why a little bit later. Of course, when we're using the laws of physics, like Newton's laws, we need a mass. So the mass of the fluid element I'll call delta M, and that's related to the volume by the mass density, which is indicated by the Greek letter rho. And in fact, rho is measured as kilograms per cubic meter in SI units. So that is the mass density of my fluid, or air in this case. And so what is the volume element? Well, it was A times delta x. So this mass element is rho, the mass density, times A, the cross-sectional area, times delta x. That's the nominal width of that element of air in the tube. All right, so now what's going to happen is if the pressure is different on the left and right side of this element, we're going to have a change in the volume of the fluid element from that difference in pressure, say at position x2 on the right side versus position x1 on the left side. And that pressure difference can be created by a passing sound wave, which we're trying to describe here. So that means we will have a different size or different volume for that element of air due to that pressure difference. So we can work out the new size, the new volume, let me call that delta V prime, after we've adjusted the positions of the left and right side of the element of air by these pressure changes. So on the left side we had a pressure P acting on my volume element here at position x1, so let's say the left face of it, and that might push the left side in by an amount delta S, and I'll put that delta S at position x1. Now likewise on the right side I have another pressure P plus delta P, and that'll push toward the left on the right side. But if it were a negative pressure, it might have pushed a little bit more to the right, and so I have delta S x2 going to the right in my drawing here. But the change in the volume would be the nominal volume, A times delta x, well, the new volume, sorry, is A times delta x plus however much I push the right side out. That kind of expands the volume, right? So delta S of x2 expands the original volume. But if delta S of x1 is pushing to the right also, that's all in the plus x direction, that is shrinking the volume because it's coming in. So I have a sign difference here. The volume changes by however much I push to the right minus however much the left side pushes to the right. And if they push both to the right the same amount, there would be no change in volume. That's what that's saying. But if the right side at position x2 increases more than the left side, that would be a larger volume. Vice versa, if it pushes less out, it'll be a smaller volume. So I'm going to label this change in volume delta V prime. And so the change in the volume size would be this delta V prime minus the original delta V, which means I'm going to subtract off this A delta X. So I had an A delta X in my delta V prime expression, and that's going to subtract off with the A delta X from earlier. And so the change in volume, delta V prime minus delta V, and I'm going to give that a change of delta of the delta V, so that's delta squared, so doubly small if you like, or the product small. And that's just going to be the cross-sectional area A times that change in displacements, delta S at x2 minus delta S at x1. Right? And as I said, if x2 pushes out more than x1, this is a positive increase in the volume size, and if it's the other way around, it's a negative change in the volume. All right, we've only been describing the volume of the element. We haven't actually brought in any physical forces, so let's do that now. So Newton's second law, you know that. It's F equals ma. For my fluid element here, it has a mass delta m, and a is the acceleration. So that would be along the x-axis. We're just doing one-dimensional propagation right now. So that would be a of x. And so if there's a force acting on this fluid element, a net force, that gives an acceleration a of x that is given by that force divided by the mass of that fluid element. Now what was the mass of the fluid element, delta m? That was rho, the mass density, times a times delta x. So that goes there. What is acceleration? Well, that's the second derivative of the position. So it's the change of the change of the position, d squared s dt squared. All right, so that's the ma part of Newton's second law. What about the forces acting on it? Well, that would be the force at x1 and the force at x2 that come into play. Now, how does the pressure work? Pressure here pushes outward in all directions, so it's on the left side, it's pushing on the left face in the plus x direction. It's pushing it, I'll draw it here, pushing toward the right. So, and to get that net force from at that position x1, that would be the pressure P times the cross-sectional area A, and that will give me the force. Now on the right side, the pressure acts in the opposite direction. It's pushing back on the left. And so that direction of that force is in the negative x direction, so it comes with a minus sign there. The pressure, though, will let be different. It's P plus delta P. And so it's P times A, that's F of x1, minus P plus delta P times A, that's F of x2, the force on position 1 and at position 2. And so the difference of that, you can see the P times A term will cancel out. This cancels with that. And I'm just going to get the negative delta PA, negative delta PA there. Okay, but how are we going to relate this to the volume change of my fluid element? Here I've got to use some more physical properties, and in particular of materials, whether it be a gas, liquid, or solid, and that is something known as hydraulic stress, or the volumetric elasticity of the material. So what happens if you apply a pressure to an object, that will change the volume of that object depending on some coefficient, and that coefficient is known as the bulk modulus of that material. So if I increase the pressure surrounding a volume of material, so let's say my volume element of air here in my tube, if that pressure increases, it will shrink the volume, that's the minus sign, in a relative sense. It's a relative change in the volume, so that in my case it's the change in the volume over the original volume itself, delta squared V over delta V. And the constant proportionality here is B, the bulk modulus, and it comes with a minus. That B is different for different materials, but for all materials there is this bit of shrinkage if you increase the pressure, or expansion if you decrease the pressure. It's just going to be a lot more for air, the expansion shrinkage versus steel, okay? All right, for the same pressure change. So that's providing our force. That was, if you like, the left side of Newton's second law, which depended on the pressure change times A. So the net force acting on my element of fluid was minus delta P times A. And on the right side should be another minus. Well, this was the net force, and the delta P here is a negative here. So if I'm plugging in for delta P, the negative times negative turns a positive. I have the term B that comes in there, and then I have A coming in here, so that A goes there, right? But then I have to multiply that by the ratio of delta squared V over delta V, the change in my volume over the original size of the volume. And so that's the expression here in the fraction. The change in volume was, again, A times the difference delta S at x2 minus delta S at x1 over A times delta X, the original volume of the fluid. Okay, so I picked up from the net force, it's delta P times A. So here's the delta P times A. Delta P was B times that change, relative change in the volume, and then there was an extra A that went here. But we'll see that, you know, two of those A's cancel out there. All right, so I'm going to switch slides, but I'll go ahead and repeat these formulas on the next slide, and so we can see where we go with this calculation that I boxed here. Okay, so let's just kind of now on a new slide summarize a bit where we were. Remember, the property of material called the bulk modulus governs by how much its volume changes for a given pressure change. That's B, and it's measured in newtons per square meter. Rho was the fluid mass density, that in SI units that's measured in kilograms per cubic meter. And yes, so here was Newton's second law, at least the force part of it. The net force acting on my fluid element, the product of B times A, and then those change in the volume over the volume itself. But the other side of Newton's law was MA, the mass times acceleration, so that was delta M times A in the x direction. Again, the x direction was going this way, toward the right. So the mass density rho times A times delta X. That's the mass density of that element of fluid. And then the time derivative of the position is d squared of s dt squared. So two derivatives in time of the position of that volume element which is at position S. So those are the two things we're going to set equal to each other for Newton's second law. Right? Okay, and so we can do that by setting them equal. So what can we do? Well, we saw both left and right side. Well, first of all, there were these areas in the fraction on the first formula that we can cancel. But I also have another area here in fx net, which will cancel the time derivative part for the delta m there. So that cancels also. So I'm left with just b. I can go ahead and divide both of these by b, the first and second equations. So that'll cancel b in the first equation. I'll use another color and cancel it. There we go. So that cancels out. And so what do I have? I have if I look at the bottom right here, I have rho over b, two derivatives of s with respect to t squared, dt squared anyway. And on the other side, the fnet side, I had the change in the position, delta s at x2 minus delta s of x1 per delta x. But there was this extra delta x I left off, so we're going to go ahead and divide that in both cases, there and there. And that means it comes in the denominator with delta x squared here. So I have the change in the position of the the right side, s at x2, minus the change in the position s at x1 from that pressure wave coming by, over the size of the volume of air, which was delta x squared, and that equals rho over b, 2 time derivatives of the position s. Okay, so what are we going to do? Well, we're going to let this volume of air, or my material, be infinitesimally small. So the width of this volume element I call delta x. We're going to let delta x become dx, just indicate that it's infinitesimal. And x2, it is larger than x1. It's on the right side and x1's on the left, but we'll let them differ by just size dx as well. So x2 is just x1 plus dx. So what we have, therefore, is if I go back to the bottom left corner here, I can take one of the powers of delta x in the denominator and put it underneath each term here. So let me just go ahead and do that. I will go ahead and kind of indicate it with like a slash dx here. And then I'll remove one power there. So I have delta s over dx, or delta s over delta x, or ds over dx. So that's the first derivative of s with respect to x, minus the first derivative of s with respect to x, but they're at different positions. So I've indicated that here. ds dx at position x2, which was x1 plus dx, minus ds dx at position x1, so just indicated there at position x1, but I had one more dx in the denominator. It was delta x that I'm letting become dx. So I have 1 over dx, and I'm going to do the thing that we usually do in calculus. We'll let dx go to 0. Well, this definition here I've written here, a function at x1 plus dx minus the same function at x1 over dx, that's a definition of a derivative. So this is a derivative of a derivative, so that's going to be two spatial derivatives of s. The right side, that stays the same. It's rho over b, d squared s dt squared. But I can replace the left side with a second derivative. Just like we had one on time on the right, I now have one on space in the left. D squared s dx squared. Now notice I've gone to the curly derivative sign. That's because these are partial derivatives. S is a function of both space and time, so the left side is a derivative with respect to x only and holding time constant. The right is a derivative with respect to time only and holding x constant. And then I had these ratio of coefficients rho over b. And the exciting thing here is that that equation in that form has the form of a wave equation. When I have two spatial derivatives of a function equals 2 time derivatives with some constant up front, solutions to that will be basically sinusoidally traveling waves, and I'll show that in a moment. So, but we can rewrite this equation to make it more explicit that this is a wave equation. I can write the rho over b as just 1 over v squared, where v is the square root of just b over rho. Remember, B was the bulk modulus, rho was the mass density. And so that is the form of a wave equation. You would have seen this, for example, in transversely propagating waves on a string. So string waves were given by an equation of this form too. But now we're not talking about strings, we're talking about a longitudinal wave, of a pressure wave going through a gas or fluid or solid, but it has the exact same form. So the solutions are going to have the exact same form. It's just a slightly different phenomenon. It's a longitudinal wave, and it's a change in pressure, not a transverse displacement of a string. But they are very similar, but here we can see we've even predicted the speed of these waves, which is the square root of the bulk modulus over the mass density. So we have a prediction even for the speed of propagation. So for such an equation, as you should have seen before, for example, for propagating string waves, is that a solution to this partial differential equation are sinusoidally varying functions. So here I wrote, for example, that the displacement in S, that's the location of the fluid element in x and t, varies sinusoidally, has an angular wave number k, and an angular frequency omega. It can be moving to the right or left, so I write kx plus or minus omega t, and there could be a phase constant. Instead of a sine, it might have been a cosine, or it could have started some arbitrary phase, so I can add a phase constant there. And there's some amplitude, which I've labeled Sm for the maximum position change. It's for any given position in time, it's just oscillating plus or minus this amplitude, or at any given time, it's you can imagine the position has moved depending where you are by plus or minus Sm in position. Okay, so that's the position of that fluid element for this passing sound wave, essentially, the change in pressure. But where does the pressure change come from? Can I get that from this equation? I've got an equation for now the solution of where the volume element is, and it's oscillating in position and time. But how do I get to pressure? Well, here I can go back to that bulk modulus equation, the volumetric elasticity of the material. Change in pressure is the negative of the bulk modulus times the relative change in volume, delta squared V over delta V. But that relative change in the volume is just going to be delta S over delta X. Delta S is the net change in the displacement of the fluid element over the net extent delta X that it extends over. And so that's just negative B, the bulk modulus, times the partial derivative ds dx, an infinitesimal amount of change in S, the position of that volume element, over X. So I can get delta P by taking this derivative of my solution for S. So that's what I'm going to do. If I do that, I get a negative B, so there's my negative B there. I have to take a derivative of S with respect to X, so I'm taking a derivative of this sine function. So first thing I note is I'm going to get Sm out as well, so that's good. I'm going to turn a sine, when I take a derivative of a sine function with respect to X, I'm going to turn that into a cosine. But that's not it. This is a function of X, but there's a function of the sine argument that depends on X, so it's k times X. So I have to apply the chain rule. And if I apply the chain rule, I have to take derivative of the argument to the sine function. So it's derivative of sine, which became cosine, and the derivative of the expression kx plus or minus omega t plus phi, derivative of that with respect to X is just k. So I'm going to pull out this extra k here from the chain rule. And so that's what I get for the pressure change. I now have a formula for the pressure change. And one thing to note is, since the displacement was a sine function, as I've written as a solution, the pressure change is a cosine function. They both oscillate. They have different amplitudes and different units, of course. But in terms of the oscillation, they're out of phase. If the volume element's moving to the right, the volume element is not, well, let's say that, moving to the right and expanding. It doesn't mean the pressure is necessarily increasing. It might be not increasing. They're 90 degrees out of phase. Basically, a sine and a cosine are 90 degrees out of phase. Of course, there's a negative here, so one's the negative of the other. But basically, I can write now the pressure formula for the solution for the pressure change due to my passing sound wave as some amplitude delta Pm. That's just going to be this bulk modulus times k times Sm. And then I can rewrite the cosine as a sine kx plus or minus omega t and just call my phase constant something different, phi prime, instead of phi. But if I wanted to relate them to each other, phi prime is just phi minus pi over 2 to handle the transformation from sine to minus cosine. And the amplitude of my pressure change can be related to the amplitude of the volume displacement, Sm, by this formula. Delta Pm is Sm, and then remember there was BKSM, so B, how do I get that from the circled formula here? I can just take the square. I have V squared equals B over rho, so V squared rho is B. So there's V squared rho, that's B times K times Sm. So that helps me get an expression now for the pressure change due to a sound wave propagating. The solution has an amplitude, and it's varying sinusoidally as a traveling wave. And it's a longitudinal wave where it's describing the pressure change. And if I wanted to relate that to the position or displacement of my volume element fluid, I have a relation here transforming between the two. Okay, a lot of math there. Hopefully that made some sense. So we've now derived both the wave equation and solutions for the pressure wave, or the displacement, if you like, displacement wave, this longitudinal wave due to sound. What did it all mean? Let me try to summarize that. So here was that last expression where I'm talking about this pressure wave. So it's a change in pressure at an amplitude and a sinusoidally varying function. And the thing to point out is this amplitude is not the absolute pressure itself. This is a change in the pressure from whatever the ambient value is. If this is a tube on the right here, if this is a tube at atmospheric pressure, delta Pm, or delta P in general, is the change about that ambient value. So it's 1 atmosphere plus or minus something. It's not going from negative pressure, which doesn't make any sense, to positive pressure. It just is going ambient, some value, like atmospheric pressure, plus or minus some small amount. So that's one thing to point out about the meaning there. The other thing is we've derived a wave equation that looks very much like the string wave equation and other wave equations. And so the usual relations for traveling waves still hold. That is that the speed of the wave propagation, which by the way we predicted, remember that was the square root of B over rho, that's also related to the angular frequency over the angular wave number of that wave, omega over k, where angular wave number is 2 pi times the cyclic frequency, and angular wave number k is 2 pi over the wavelength lambda. Or in other words, the speed of the wave v is equal to the product of the wavelength times the frequency, lambda times f. So that still holds also. Now, what kind of speed are we getting for these waves? Well, if we're talking about air at room temperature and standard pressure, so on the Kelvin scale, the temperature of 293 degrees Kelvin and 1 atmosphere, then the speed that you get is 343 meters per second, which is about 765 miles per hour. Quite large, right? Very fast speed, but not infinite either, and certainly there are aircraft and rockets that can break that speed. Now, the way we get that speed of 343 meters per second is we can take this formula that was predicted that the speed was the square root of the bulk modulus over the mass density rho. For air at STP, standard temperature and pressure, it's 1.2 kilograms per cubic meter, and the bulk modulus was 1.42 times 10 to the 5th newtons per square meter. And using that formula, so that's how we get that. And finally, just to illustrate this relation here between the speed and the wavelength and frequency, if we're again at standard temperature and pressure, if we have a sound with a frequency of 1 kilohertz, which is in the normal hearing range of humans, that corresponds to a wavelength of this longitudinal pressure wave of 34 centimeters. Okay, that ends this lecture on the derivation and solutions to the sound wave equation.